Hello everyone, I'm Hao Xu. My title is Optimization of Downlink Power Allocation in NOMA OTFS based cross-domain Vehicular networks. I will report on the following 5 areas: abstract, system model, SEC, power, allocation, strategy, and system simulation. OTFS and NOMA are pivotal for enhancing the transmission performance of vehicular communications. This paper dives into the downlink power location of NOMA OTFS system with a frequency domain linear equalizer with a high-speed user in DD domain and multiple low-speed time frequency domain NOMA users. We present a problem based on NOMA user fairness and give 2 low complexity solution schemes. And first, we focus on the downlink of NOMA OTFS vehicular communication system in this paper, where a base station serves a DD domain high-speed users with OTFS modulation and multiple TF domain low-speed users in a manner similar to traditional OFDM, and assumption a signal BS communicates with PS1 users include the high-speed user V0 and the low-speed user UI. We can get a NOMA user group considering the multipath transmissions. The DD domain channel, response for each user is represented to this formula. And after ISFFT, the signal of V0 in the DD domain can be transformed into TF domain as the first and the second formula. The NOMA user signals are pieced directly in the TF domain, each of which occupies a sub-frequency channel and receives n information bearer symbols. And when NOMA is used for transmission and multiple users share the spectrum resource, and each user receives the signal in the TF domain at the receiving end as the first formula. And the BS since XANM after the Heisenberg transform and after transmission. The TF domain receives the signal of I's user at the second formula, where beta 0 and beta I is the power allocation of V0 and UI. And the signal of V0 has significant intensity in the DD domain, which should be demodulated first. And the NOMA user signal can be treated as a noise through a SEC. The received signal of user V0 and the DD domain in the DD domain is written as the first formula, and it can transform to the second formula. Then we can define vector Y0KHS and Y0HS as follows. And the received signal vector of V0 is the first formula, where H0DD is the channel gain vector, which can impressionize this matrix. And we use the FDLE, which consists 2 steps. Step 1, we can detect high-speed users signal and substitute the detection matrix as the first formula. Then by multiply this matrix, we can get the second formula. After a series of mathematical derivations, we can get the SNR of V0 is as the first formula, and step 2 is detect the NOMA user signals, and we first detect the signal of V0 in the DD domain. After demodulation, the NOMA user signal can proceed in the DTF domain. Assuming that NOMA user's channel are time invariant, we can simplify the channel of the ICE user as the third formula. And similar to the detection of the high-speed user signal in step 1, the signal of NOMA user after adding the detection matrix is the first formula, and multiply this matrix for YL hat to obtain the received SNR of high-speed user at UI as the second formula. For sec, in the following, the NOMA user must successfully decode the signal of V0 with the assumption that the signal of V0 is successfully demodulated and can be moved. The NOMA signal of UI in the TF domain is obtained as the first formula. And since the signal of UI is only related to YI n I-1, the SNR of NOMA user UI can be detected by a single top equalizer as the second formula. Then, in the downlink NOMA OTFS vehicular system, considering the cross-domain transmission, power allocation can be based on 3 objectives. 1. Ensuring the high-speed user meeting is QoS and target rate R0. 2. Guaranteeing the NOMA users can successfully decode the signal of the high-speed user. 3. Ensuring successfully signal detection of the NOMA users, and then the optimization problem as the first formula. Then, since the optimization problem is non-convex, so auxiliary variable is introduced to transfer the original problem into a constant one as the second formula. Then the table one is IPAO algorithm, and we can use it to obtain the optimal solution to the problem. And then we give a superposition 1. For the maximum power allocation, we aim to get equal bit rate for all NOMA users. And then we can use it to achieve a closed form solution for the optimization problem with the following steps. Step 1. We can set total power, PT, and the channel state information. Step 2. To calculate the allocate power for the high-speed user while meeting the QoS, the convenience of SAC, and the total power constraints, we can perform the following procedure and give the total power constraint and non-negative power for the NOMA user. The final power allocation for the high-speed user is determined as this formula. And step 3. After determining the power of V0, the remaining power can be allocated to NOMA users. The allocated power for the ICE user becomes the second formula. And this assumption provides a reasonable starting point and makes more feasible derivation of the closed form solution. And the table 2 is simulation parameters, and in this section, Monte Carlo simulation is performed for the proposed power allocation schemes in the NOMA OTFS Vehicular system. As shown in Figure 2, both of the proposed power allocation schemes show the significant advantages in rate distribution compared with the equal power allocation strategy. Both schemes ensure the rate fairness among NOMA users under different transmit SNRs. And we compare the NOMA users' minimum bit rate under different power allocation policies, and NOMA user numbers is in Figure 3. The proposed IPAO and OPA outperform both EPA and CSIPA strategy, and the OPA stream achieves the maximum system bit rate with minimum complexity, and the fixed power allocation yields decreased minimum rates with more users, which is due to the total power constraints. And then Figure 4 shows the minimum bit rates of NOMA users for OPA policy with different modulation modes and QoS constraints of V0 with 3 NOMA users. We used the appropriate channel coding scheme. It is seen that the cost of 16 QAM outperforms the cost of 4 QAM since it transmits more bits per symbol, as the QoS constraints of V0 intensify. The minimum rate for NOMA users diminishes due to increased power allocation for QoS of V0, and in the low SNR regions, this depletes the power of the NOMA users, which further impacts the accuracy and performance of SAC. When without rate constraints of V0, the high-speed user will not influence power allocation, and the NOMA user's rate peaked. And that's all. Thank you very much.